Today, we're digging into a specific example of how to apply kinematic equations to a real-world problem. Or maybe I should say a real out-of-this-world problem. Because today, we're going to see how they can apply to the launch of a rocket ship. It won't be easy, but whoever said rocket science was easy? Then, once we find the acceleration of the rocket ship from kinematics, we'll see how the newest model of the Lamborghini Revuelto sizes up in comparison. Before launching into the details, you'll first need to know what the kinematic equations are and where they come from. I covered that in a previous video, and in case you missed that, I've linked it in the description below. And then we'll be able to figure out which accelerates fastest. And if rocket ships and Lambos aren't your cup of tea, there's a second kinematics problem at the end of this video. So you'll be able to figure out how to use a car's skid marks as a polygraph machine. So strap in, grab a space pen, or maybe just a pencil, and let's get started. Hi everyone, this is John, and welcome to my channel, drjohn.dev. I have a PhD in physics and have been helping students solve problems in physics for over 15 years. Make sure to subscribe to my channel and hit that like button. So now that we're armed with the kinematic equations, let's see how they can be applied to the launch of a rocket ship. Let's take a look at the July 4th, 2006 launch of the Space Shuttle Discovery. This now retired American spacecraft flew more flights around the Earth than any other orbiter built by NASA's Space Shuttle program. During its tenure, Discovery launched 39 times, completed 5,830 full Earth orbits, and had flown 149 million miles around Earth. To reach orbital speed around the Earth, the shuttle must accelerate its 78 metric ton body to a speed of 17,500 miles per hour, or just over 7,800 meters per second. And it does all of this in just 8.5 minutes. To find the rocket's acceleration, you may be tempted to just find its change in velocity from rest and then divide by 8.5 minutes. As I warned before, the kinematic equations we derived assume a constant acceleration. So we can't blindly assume the rocket's entire 8.5 minute ascent into orbit has a constant acceleration. In fact, the launch is quite dynamic. On the launch day, the main Discovery orbiter is attached to 2 solid fuel rocket boosters, as well as a main fuel tank containing a fuel mix of both liquid oxygen and hydrogen. The burn rate of the liquid fuel is controlled by a throttle valve, which controls the flow rate between the liquid fuel tank and the shuttle's 3 main combustion engines. The throttle valve is controlled by the onboard astronauts. When the throttle valve is constricted, or throttled down, less fuel is burned by the engines, and the rocket accelerates at a slower rate. When the throttle valve is slowly opened wider, or throttled up, the rocket has more thrust and hence accelerates at a faster rate. So you may be asking, why are we even considering a rocket launch if the acceleration isn't going to be constant? Well, there's a workaround here. Think about how the curves of a circle can look like straight lines if you zoom in and make x small enough. Analogously, a velocity curve with a non-uniform acceleration can be approximated as a straight line if you zoom in on small enough intervals of time. That is to say, acceleration can be treated as a constant as long as the velocity looks like a straight linear curve during that small time interval. So, we simply need to obtain the rocket's velocity versus time data, and we can analyze the acceleration for small periods where the velocity curve isn't bending and looks like a straight line. Wait a second. Where am I going to get the velocity launch data of the Discovery rocket ship? I have an idea, but I'm not sure if this is going to work. Houston, we have a problem. We need some launch data from one of the spaceship Discovery launches. Can you send that over? Over?
Okay, let's go for auto sequence start.
Houston, do you
Discovery is ready. The weather is beautiful. America is ready to return the space shuttle to flight, so good luck and Godspeed, Discovery.
Wow, that's great. It looks like we're really going to be seeing a launch after all. Let's pay attention to that velocity data as it comes in.
10, 9, 8, 7, 6. Go for main engine start. Main engine start. 2, 1. Booster ignition and liftoff of the Space Shuttle Discovery, returning to the space station, paving the way for future missions beyond.
Discovery's 3 liquid fuel main engines now throttled back to 67% of rated performance, reducing the stress on the shuttle as it breaks through the sound barrier. Discovery already 3.5 miles in altitude, 1.5 miles downrange, traveling almost 750 miles an hour. Everything looking good on the bird.
Okay, I hate to pause a live flight, but just a quick recap on the initial launch phase. All 3 main rocket engines, as well as the 2 booster rockets, are operating in tandem. But, as the commentator announced, the throttle is dialed back to just 67% of its operating performance. You might think the rocket would accelerate the most at its initial launch, but this isn't the case. Because Earth's atmosphere is densest closest to the surface, the rocket ship experiences the most atmospheric stress during this phase of the launch. To prevent damage to the ship, the acceleration is dialed back. But once it reaches a high enough altitude, the ship can begin accelerating faster. Let's take a look.
57 seconds into the flight, engines beginning to rev up.
Watch the velocity begin to curve upward as the engines are slowly revved up and the throttle is gradually opened.
Discovery Houston, go at throttle up.
The opening of the throttle brings more fuel to the 3 main combustion engines, and hence increases the rocket's thrust. Thus, the velocity continues to increase at a faster and faster rate, and continues to curve upwards. Until the rocket's solid rocket boosters begin to deplete their fuel supply. As the solid fuel begins to deplete, these boosters provide less and less thrust. So, although the velocity is still increasing, it does so at a slower rate. After the solid fuel boosters have burned off all of their fuel, they separate from the Discovery shuttle, as we can see soon.
Standing by for solid rocket booster separation. Solid rocket booster separation confirmed, guidance now converging.
To save time, we'll speed things up a bit, but watch for any periods of time when the velocity looks approximately like a straight line. This period of the launch should have a smoothly changing velocity, but still not quite linear. During this time, the mass of liquid fuel being consumed is equivalent to draining an average-sized swimming pool every 25 seconds. So, even with a constant thrust, the shuttle will continue to accelerate faster and faster due to its constant decrease in mass.
Standing by for main engine cutoff. That will be followed a few seconds later by the separation of the external fuel tank.
As the commentator announced, once the Discovery reaches its required orbital speed, it will shut off its main engines and then separate from its liquid fuel tank.
The booster officer reports that we have main engine cutoff, standing by for external tank separation. External tank separation confirmed.
And there you have it, the velocity versus time curve of a rocket launch. By the end of the launch, the Discovery has reached its orbital speed, which clocks in at around 17,500 miles per hour, or 7,823 meters per second. So where would be the best time interval to analyze with the kinematic equations? If you take a look towards the end of the launch, just before the main engines are turned off, you may notice the curve is quite straight, and aligns pretty well with a straight line. We can choose 2 points along this line, and we can be confident that the acceleration between these 2 points will be constant. Reading the values from the graph, the first point clocks a velocity of 6,070 meters per second at 450 seconds. And the second point clocks a velocity at 7,523 meters per second at 500 seconds. We can grab this data and head to the whiteboard. So when presented with a kinematic problem, it's always a good first step to label the information presented in the problem statement with the relevant kinematic variables. Here, we're given the initial time of 450 seconds, so we can label this as t0. We are also given a velocity at that time, so we can label this quantity as the initial velocity, v0. We are then provided that at the time interval of 50 seconds later, which we can label as delta t, the rocket's velocity reaches 7,523 meters per second, which we can label simply as v. We aren't provided with a final time, or the acceleration, which is what we are trying to find. Once we have labeled our variables, we can take a look at our three kinematic equations and determine which equation best links all the known and unknown variables together. Since we weren't provided with the rocket's displacement, or even asked to find it, we can choose the first kinematic equation, which is v of t equals a times t plus v0. Before moving forward, it's important to understand which value of time t to use for this equation. Do we use our initial time, t0, which was 450 seconds? Or do we need to find and use the final time, t sub f? Or do we use the net time interval, delta t, of 50 seconds? Think back to our derivation of this equation. In our integration over dt, we integrated from an initial time of t equals 0 to a final time of t. And after integration, the result is the final time t minus the initial time t0, or put another way, delta t. So, when applying this equation, make sure to use the net time interval, delta t. Situations like these are what make understanding the derivations of these equations important. Without knowing how the equations are derived, you're taking a huge risk of applying them incorrectly, and eventually running with scissors. So once we have chosen the appropriate kinematic equation for the problem, we next need to algebraically solve for our unknown, or in this case, the acceleration a. And after solving for a and substituting in the given values for v, v0, and t, we find the acceleration of the discovery to be equal to 29.06 meters per second squared. Now, this is a very large acceleration, and to gain some intuition on how large this acceleration is, rocket scientists typically compare a rocket's acceleration to the gravitational acceleration due to Earth, which is equal to 9.8 meters per second squared, and symbolically is labeled with a g. Because of this labeling, this ratio is often referred to as the g-force of a rocket. But make no mistake, it's not really a force at all. It's an acceleration. Regardless, to determine how many g's the Discovery experiences during this stage of the flight, we can divide the rocket's acceleration by the acceleration due to gravity, and we can find this to be equal to 2.97, or 2.97 g's. So an astronaut on board the Discovery would weigh almost 3 times their normal body weight during this stage of the launch. Because of this extreme, the Discovery's main engines are actually throttled down during this final phase of the launch to stay below the 3G threshold and prevent harming the astronauts on board. The active tuning of the engines to stay below this 3G threshold is actually the reason why the acceleration is so steady and constant during this final stage of the launch. To gain a little more perspective on how the acceleration changes during the launch, we can find the entire acceleration curve by differentiating the velocity versus time data. Pretty non-uniform, huh? Notice the only real constant acceleration during the entire launch was during the time interval we analyzed, which also happened to be the largest acceleration during the Discovery's ascent into orbit. Remember, this was a design feature of the ship and put in place for the interest of safety for the onboard astronauts. Comparing the acceleration with the velocity, notice how much more distinct the stages of the launch appear on the acceleration curve. you can clearly see the sequence of the launch, beginning with the high atmospheric stress period, followed by the throttle up in the main engines, followed by the depletion of the solid fuel rocket boosters, and then, after ejecting the boosters, the smoothly changing acceleration period until main engine cutoff and ejection. This really demonstrates the power of knowing the acceleration curve for any object in motion. Now, how does the Discovery's max acceleration compare to something a bit more down to earth? But not that much more down to earth. As I said in the beginning, we want to compare this to the newest line of the Lamborghini Revuelto. Clocking in at a max speed of over 350 kilometers per hour, or around 28 meters per second, the Lamborghini Revuelto is quoted at accelerating from 0 to 100 kilometers per hour in just under 2.5 seconds. So which one has the fastest acceleration? Well, for the Lamborghini, I think it's safe to assume the newest model isn't ejecting any rocket boosters during its test run. And the mass of the fuel consumed in 2.5 seconds is pretty negligible when compared to the mass of the car. So while it still might not be exactly uniform, the acceleration should be pretty close to a constant while the car speeds up from 0 to 100. So we can simply apply our kinematic equations to the entire time interval of 2.5 seconds. As we did before, we can label the given parameters with the relevant kinematic variables. We can set the initial velocity of v0 equal to 0 meters per second. And since we weren't provided an initial time, we can set the initial time t equal to 0 seconds. This way, our final time at t equals 2.5 seconds will be equivalent to delta t, which, as we saw before, is what we need to use in our kinematic equations. Next, we can set the final velocity v equal to 100 kilometers per hour. We want to find the acceleration again, so we can use the same kinematic equation, v of t equals a times t plus v naught. Now, solving for a and plugging in our values for v, we must be careful. Remember, we eventually want to make a fair comparison to the rocket's acceleration, which is in units of meters per second squared. So we need to find the acceleration of the Lamborghini in units of meters per second squared. And in order to do this, our velocities must be in units of meters per second. So we need to make sure to convert our velocity from kilometers per hour to meters per second. If you need more explanation on how to convert units, check out my previous video on that topic, linked in the description below. And after making this conversion, we find the final velocity to be equal to 28 meters per second. So after making all of the appropriate substitutions, we find the acceleration of the Lamborghini to be 11.2 meters per second squared. So comparing with the Discovery, the Lambo accelerates less than half as fast, but it's still pretty quick. We can also determine the g-force of the Lamborghini, which evaluates to 1.14 g's. Any car accelerating above a g is definitely breaking some kind of traffic laws. Before moving on, let's make one final comparison. Dividing a rocket's acceleration by g may be the standard metric for space aeronautics, but we can invent our own new system of measurement. So, dividing the rocket's acceleration 2.97 g by the Lambo's acceleration of 1.14 g, we find the Discovery's acceleration to be 2.61 times the acceleration of a Lamborghini, or a sub Lambo. Yes, the Lambo force is certainly strong with this one.
Knowledge.
Moving on. The last problem of this video is a bit more challenging in assigning the kinematic variables, but the general approach of organizing your known and unknowns and then applying the appropriate equation is the same. Let's take a look. This problem involves a car that slams on its brakes and crashes into a stopped car at a red light. The driver of the moving car claims he was traveling at the speed limit of 65 miles per hour and just couldn't stop in time. The skid marks of his car are measured to be 400 feet, and the road conditions are determined to cause a max deceleration of 7.35 meters per second squared. The question asks, was the driver telling the truth? What was the minimum speed of his car just before slamming on the brakes? The main challenge of this problem is deciphering the numerical values and assigning them to their corresponding kinematic variables. At a quick first pass, it's tough to assign the length of skid marks and road conditions to the variables in our equations. But let's break it down. First, we know the moving car must be traveling at some initial velocity, so we can label this as v0. This is what we're trying to find. The car then slams on its brakes when it sees the stopped car. When the wheels are locked by the brakes, the friction between the road and the tires is the only contribution to slowing the car down. So the car therefore slows down by 7.35 meters per second squared. And we can make the sign of A negative since it's decelerating. We also know that a locked tire against the road will leave behind skid marks. So the length of the skid marks represent the length that the car traveled while decelerating, or delta x. Finally, we weren't given the final velocity when it collided into the stopped car. But if we assume this velocity is exactly 0 meters per second at the time of the collision, this will give us an absolute minimum speed the car must have been traveling before slamming on its brakes. If the car were traveling slower, the deceleration from the road would stop the car before it would be able to collide. So for the minimal speed of the car, let's assume the final velocity to be 0 meters per second. Organizing our kinematic variables now, we know the final velocity, v final, the net displacement, delta x, and the deceleration, a. And we're trying to find the initial velocity, v0. As we did before, we can now choose the kinematic equation that most succinctly relates these quantities together. The third kinematic equation does the best job in this case, which is v squared equals v0 squared plus 2 times a times delta x. Since we are trying to find v0, we can solve this equation algebraically for v0. After taking the square root of both sides, the negative inside the square root sign might look a little scary. But remember, the sign of the acceleration is also negative. So when we substitute this in, the negatives will cancel. In any physical problem, if you're consistent with your sign convention, you won't run into any problems. Unless it's a result not based in the physical world. In which case, good luck. And one final item of housekeeping. We also need to convert the 400 feet into meters so that it can be correctly multiplied to the acceleration in units of meters per second squared. So, after all of the dust settles, this brings the car's minimum initial velocity v0 to 42.34 meters per second. Now, this definitely sounds fast, but how does it compare to 65 miles per hour? In order to answer the question completely, and for our own understanding, let's convert this answer from meters per second to miles per hour. This brings the car's minimum speed just before slamming on the brakes to 94.7 miles per hour. So, to answer the question, was the driver telling the truth? Absolutely not. The driver was traveling at least 30 miles per hour faster than the speed limit of 65. That pretty much wraps up the key lessons on kinematics in one dimension. Thanks for watching, and let me know what you learned in the comments below. What would be another worthwhile example to try explaining with kinematics? In the videos ahead, we're going to spend some time with vectors before then heading into two-dimensional motion. Consider subscribing to my channel, and be sure to hit the like button if you like this video. And until next time, happy learning.